in general, where do you weigh in on the state of quantum gravity research? Since I'm guessing that this is one of the areas, even though I don't think we've used that term yet, where you think there really is a crisis.
Well, no, look, the problem is quantum gravity is where the region where quantum mechanical effects impact on gravity is a region that's so far removed from anything you could directly test in the laboratory. Gravity is the weakest force in nature in the first place. It's hard to measure classical gravity at a fundamental scale. Quantum gravity effects are on unbelievably small scales. The only places they're relevant, and I mean it, probably, the only places they're relevant are the final stages of collapse of a black hole and the very beginning of the universe. Other than that, quantum gravity probably is irrelevant. General relativity works fine. But I actually have worked on quantum gravity recently. I wrote a paper at Nature recently, Nature Physics Reviews, with some colleagues from Europe, thinking about ways you might test quantum gravity by looking for analogs in condensed matter systems. You know, black holes have a horizon because the escape velocity is faster than the speed of light, where you can create, and that results in something called Hawking radiation. Hawking first realized when you consider quantum effects. And looking at certain classical fluids, or not necessarily classical, semi-classical fluids, or even quantum fluids, in condensed matter systems, people have created analogs of black holes where you can measure Hawking-like radiation. And so I wrote a paper thinking about whether you might be able to probe other features of quantum gravity by appropriate condensed matter systems. So you might analogs. And of course, they're always analogs, so you'll be able to just get ideas of what effects may or may not be important. It's not quantum gravity directly, but it might be useful if we're trying to understand how to probe it. So I have thought about that a little bit, but on the whole, it's kind of a sterile enterprise, because that's why string theories have such problems, because the areas where you're going to correct classical general relativity are areas that are so far removed from anything generally we could directly detect that it makes it extremely difficult to imagine how the theory would be validated, or how you'd even do the right theory.
So your idea would be that rather than to generate a theory first, like string theory, and then perform experiments based on it, which we don't have the energy to do, it would be to go into something like a condensed matter system and try to find first data, and then...
Well, it may not be either or. That's the point. It's just you look 1,000 points of light. You look everywhere you can. So string theory, directly, and there may be experiments you can do, but this is another approach. So it's not either or, I think. It's just you're flailing around and you look at anything you can find. You look under where the lamppost is. I've used that analogy many times, right? If you're drunk and you come out of a bar and you've lost your keys, where do you look? You look under the lamppost. Not because they're there necessarily, but because they're the only place you'll find them if they're there. Anyway.
So granted, though, that the quantum gravity effects are extremely small and there haven't been experiments to test the various theories, does that mean that you're pretty much agnostic on all of them? Agnostic on string theory, loop quantum gravity, causal set theory, all of these things? Or do you have any horse in the race?
I'm generally an agnostic about everything, but I do
We're
think...
an anti-theist. I heard...
I used to be. Now, that's because my friend Christopher Hitchens used to say that, and I like the idea. But I'm much more of an apatheist. I really don't give a damn. I mean, God is irrelevant to me, so I don't even think about the question. So an apatheist is my theism. But when it comes to different theories, there are ones that I find potentially more likely, or at least more well motivated. And I happen to think string theory is more well motivated than loop quantum gravity. So, but that, and I think it's also had a bigger impact on the rest of physics than loop quantum gravity has, because it's developed new kinds of mathematics. That doesn't mean loop quantum gravity won't someday be useful. And I talked to Carlo Rovelli, and who's convinced that it is. I'm not, but yeah. So I had preferences, I'd bet. If I had to bet, I'd bet on string theory over loop quantum gravity, but I wouldn't bet a lot of money on either of them. It's there's a famous story of it was about another speculation in physics, and it had to do with my late friend and mentor and colleague Steven Weinberg, who won the Nobel Prize. And It's a remarkable physicist. And I think it was about inflation, and I think it was, someone said, would you bet would you bet your life, or would you bet your oldest child on inflation being true? And Alan Guth said one thing, maybe he would bet this, but he wouldn't bet his old child. Andre Linde said he'd bet his oldest child, and Stephen Weinberger said, I would bet Andre Linde's oldest child, which I thought was a good anyway. But yeah, so I think the point that people don't realize is most theories are wrong. Most theories are wrong. If they weren't, anyone could do it. I mean, I've written hundreds of scientific papers, and some of them are really beautiful theories, but nature chose not to adopt them. And, you just keep plugging away. And if every paper you came up with was right, it would just be almost boring.